Welcome to this presentation. I am Ranga, Associate Professor at Clemson University. This work is mainly done by my former PhD student, Pengfei Zhou. This is a collaboration with the researchers at Pacific Northwest National Laboratory. The problem we are looking at is the new threat in HPC. It initiates workloads like cryptocurrency mining have been increasingly exploiting powerful GPUs that are supposed to be used for HPC workloads. And this problem needs to be addressed timely with a solution. Our approach leverages identifiable patterns of HPC workloads. We treat illicit workload detection as a classification problem and devise RNN models to infer workloads from high-level profiles. Our contributions include an online illicit workload detection suitable for practical use and also be accurate. Our techniques handle data heterogeneity, irregularity, and losses in input data, and to enable such accuracy. And we have advanced modeling for inference accuracy. From about 2 decades ago until today, we see increasing illicit computations begin running on HPC systems. These illicit computations include crypto mining, password cracking, and the denial of service attacks. They share common characteristics. For example, they are either for-profit or malicious attacks instead of science discovery and engineering innovation. They are resource intensive, requires powerful GPU accelerators, and they use system for a very long time, from days to weeks or longer. These are the risks and issues to HPC. For example, they deprive mission-critical applications of computing cycles, make them wait in the queue for a long time, and then there are data leaking and system damages. If they are malicious attacks, they are empowered. This is a unique and a new threat that traditional security measures cannot guard against. So for example, if they penetrate the login nodes of HPC systems, then they are able to use the computer nodes because HPC systems only protect login nodes. In addition, authorized users can run illicit computations, so authorization and authentication didn't work for them. In addition, because HPC systems take performance as the first priority as a result, there are little barriers and guards against such threats. Some measures are placed on hosts, but then these threats can mask computations on CPUs and then offload the computation to accelerators. So because of these reasons, we need novel security measures to detect illicit computations in HPC on the GPU side, not on the CPU side. In this work, we take some opportunities. One major opportunity is that we recognize HPC workloads have unique patterns identifiable by advanced machine learning technology. For example, Studies have shown a small set of programs with specific resource usage patterns, 7 kernels and 7 applications represent 50% of the HPC workloads. And then they invoke certain kernels and functions like linear algebra, FFT, and so forth. This figure shows the lower level differences between HPC workloads and authorized HPC workloads and unauthorized illicit computation. We see that the illicit computation has shown very different patterns from HPC workloads. Nevertheless, these are the lower-level hardware events collected from hardware event counters. If we wanted to develop an online detection software, we cannot use performance counters. This is because then the performance counters are used at the application level, and then they are intrusive to user applications. In addition, we cannot collect many events because GPUs have only a few number of events. However, the accurate machine learning models need many of them as input. So to address this problem, we developed our own approach. So basically, our idea includes, we take illicit GPU computation detection as classification problem. Second, we only use lightweight common system level profiling for model input, and then we use multiple input sequences for inference accuracy, because one single sequence have limited information. The last, we have synergistic multiple RNNs to handle complex heterogeneous input. RNNs are well known for processing time series data. So on our GPU systems, we are able to collect the input sequences. This figure shows the overall design. So this part is the profiling, and then we have data processing online, and then we have these two different types of time series. One is a periodic data from driver runtime, the other is periodic data from resource utilization. Given these two different types, we have two different OSTM RNN models, and we fuse them as one single model, and then our model tells whether the application is authorized or unauthorized. So next, I'm going to provide more details about what kind of data profiling we need, and why we have different LSTMs and what do they do, and how they are put together. So our model first needed to address the data heterogeneity, because we have to collect multiple time series data to improve model accuracy. Then we have different kinds of data. This picture shows the top part is the periodic information about resource utilization. For example, power utilization, GPU utilization, memory bandwidth, and so forth. That's collected periodically. And the bottom part is time series data from GPU driver. So those are the events, not periodic. So they happen when the kernel or data transfers happen. They are different types of sequence because they are simply different types of data, different timestamps and so forth, and then they are synchronous. The second is the irregularity of the event-based data sequence. Unlike the resource utilization, the events data sequences happens at the arbitrary time. So we need to process them in order for our LSTM to use. The second challenge is the sample losses in utilization data. When we collect resource utilization, even though we have periodical data, however, different applications are going to have different actual sample rates, even though we give the same sampling interval. So for example, in this picture, we show that on average, data losses is about 30%. The losses depend on application and the sampling interval. The more compute intensive the application is, the bigger losses it is. Also, the smaller sampling interval it is, then the bigger losses it is. So this creates a problem because when we use different data from different applications for model training, then these data are going to be different. So we need to make sure they are at the same sampling or the actual sampling rate. So to address these challenges, we create different LSTMs. So the first part, we show a split layers for event-based driver runtime. Basically, our idea is we separate events, the type of events, to two subtypes. One is the kernel events, one is data events. So kernel events include the start time, duration, the sizes of the kernel, and data transfer includes starting time, duration, direction, and bandwidth. So for each different subsequences, we create OSTM and then merge them together. So we call them split layers. And then for the data losses, we use interpolation layer. For the resource utilization sequences, the basic idea is if we see missing data, then we are going to use linear interpolation to make up the data. This is better than the default zero padding in LSTMs. So putting these two LSTMs together, we have the final model as we shown earlier. Next, I'm going to talk about the model training and the validation. We have used the 87 authorized workloads to create training data. In addition, 17 unauthorized applications collected from GitHub and Bitbucket that include crypto mining, password cracking, brute force attacking, and so forth. We also take into account different input size and so forth. We collect the data, use NVProf and NVIDIA SMI. So the first is the periodic resource utilization include power, core utilization, memory footprint, memory bandwidth. The second type is event-based driver runtime, include kernel events and the data transfer events. In addition, we collect hardware performance counters for counterpart comparison and evaluate our model. We evaluate on 3 generations of GPUs, K40, P100, and V100. And here is selected evaluation results. We have many evaluation results, but here we only show the first is the accuracy. We show that if we only use events, and then for scene applications, they are pretty accurate, but for on-scene applications, the accuracy is less. If we only use resource utilization, on K40s, scene applications has highest accuracy, but accuracy decreases on newer generations. On-scene applications are better than events. If we use both kinds of events, both kinds of data series, then overall we have better accuracy. Accuracy is just the one part of the story. We also evaluate false negative. Here means that an application is not illicit application, but our model indicated it is. So in this case, the smaller number it is, the better. So we want to keep the false negative rate low. We see that if we use events for on-scene applications, the negative rate is high. If we use resource utilization, on-scene applications is much, much better. And if we combine them, these two sequences, the false negative rate is the smallest it's the smallest. So they have synergetic effects. We compare our model with existing hardware monitor-based workload detection. We see that if we use hardware metrics, we have comparable accuracy. However, we have better false negative rate than hardware metrics. Please pay attention that hardware metrics-based modeling is offline modeling. They cannot be used for online detection. So our is online and has comparable accuracy and better false negative rate. So in conclusion, we see there are new threats in HPC. The illicit computations take execution cycles and empowers attacks. And in this work, we propose the online detection algorithm and a model is based on lightweight profiling, and it can accurately detect with fused LSTM, use multiple data sequences. Our major findings include that illicit workloads have different patterns from HPC workloads. This fact can be leveraged for detection. We see that even though one single high-level profiling is not sufficient for accurate detection, but the multiple profilings are sufficient for accurate detection. Because multiple sequences are heterogeneous, as complex, then we need fused RNNs to model and model the work nodes and detect illicit computation. And this is all. Thank you.